This dot cannot move. The ground beneath it looks perfectly flat in every direction. But watch what happens when we change our perspective. There, a hidden downhill path, invisible from where the dot was standing. The algorithm that finds that escape route is the same one that trained every major AI model on the planet. It's called gradient descent, and it is beautiful. Before we can descend, we need a landscape to descend through. Imagine you're training an AI model and it has just one adjustable number, a single parameter, which we'll call theta. For every possible value of theta, we can measure how badly the model performs. That measurement is the loss function, L of theta. Up here, the loss is high. The model is making terrible predictions. Down here in this valley, the loss is low. The model is performing well. Training an AI model means finding the value of theta that sits at the bottom of the deepest valley. Now, real AI models don't have one parameter. They have millions, sometimes billions. But let's start with two. With two parameters, theta 1 and theta 2, the loss function becomes a surface, a mathematical terrain with peaks, valleys, ridges, and saddle points. We can color this surface by height, red for high loss, blue for low loss, creating a topographic map of model performance. GPT-4 has roughly 1.8 trillion parameters. Its loss landscape isn't a 3D surface. It's a landscape in a space with 1.8 trillion dimensions. We cannot visualize that directly, but the fundamental geometry is the same. Think of it this way. Even though you can't see a trillion-dimensional mountain range, you can still find the lowest valley if you always know which direction is downhill. And that's exactly what the gradient tells us. In one dimension, the slope of a curve at a point tells you the direction of steepest ascent. If the slope is positive, the curve is going up to the right. If negative, it's going down. In two dimensions, we need two slopes, one for each direction. These are called partial derivatives. Stack these partial derivatives into a vector, and you get the gradient, written as nabla L. Here is the key property. The gradient always points in the direction of steepest ascent. So the negative gradient, simply flipping the arrow, points in the direction of steepest descent, the fastest way downhill from wherever you stand. We can visualize this across the entire surface. At every point, an arrow shows the downhill direction. Notice, the arrows are longer where the surface is steep and shorter where it's nearly flat. The gradient tells you not just the direction, but also how steep the slope is. That information is going to matter enormously. Now we have everything we need. We know where we are, our current parameter values. We know which direction is downhill, the negative gradient. So the update rule is elegant in its simplicity. In plain English, take your current position, compute the gradient, take a step in the opposite direction, repeat. That alpha, the Greek letter alpha, is the learning rate. It controls how big each step is. We'll explore it in detail shortly. Let's watch gradient descent in action. Step 1. Compute the gradient at our current position. It's positive. The curve slopes upward to the right, so the negative gradient points left. We take a step. Step 2. The gradient is still positive, but smaller now. The slope is gentler, a smaller step. Step 3. Step 4. Step 5. Each step brings us closer to the minimum, and each step gets smaller as the slope decreases. After about 15 steps, we've essentially arrived. The same process works in higher dimensions. On our 3D surface, the dot follows the negative gradient at every step, tracing a path down the mountainside toward the nearest valley. The learning rate alpha is perhaps the single most important hyperparameter in all of machine learning. Too large and training explodes. Too small and training takes forever. Let's see why. With a learning rate of 0.8 comma, watch what happens. The step is so large that we overshoot the minimum and land on the opposite slope. The next step overshoots again, even further. The dot is bouncing back and forth and the loss is actually increasing. This is divergence. Now alpha equals 0.001. The dot barely moves. After 100 steps, we've hardly made any progress. Technically, it will converge, but it would take thousands of steps to reach the minimum. With alpha at 0.05 comma, the steps are large enough to make real progress, but small enough to converge smoothly into the valley. In practice, researchers often start with a larger learning rate for fast initial progress, then gradually decrease it as training continues, like taking big strides when you're far from the valley, then careful steps as you approach the bottom. This is called a learning rate schedule. But the learning rate isn't the only challenge. Even with a perfect learning rate, vanilla gradient descent has a fundamental weakness. Remember our stuck dot from the opening? This is a saddle point. The gradient here is exactly 0. 0 in the x direction, 0 in the y direction. As far as the gradient can tell, we found a flat spot, but it's not a minimum. It's a minimum along the x-axis. The surface curves upward, but a maximum along the y-axis. The surface curves downward. The mathematical tool that distinguishes saddle points from true minima is called the Hessian matrix, a matrix of second derivatives. At a minimum, all eigenvalues of the Hessian are positive. At a saddle point, some are positive and some are negative. Here's the critical insight for AI. In high-dimensional spaces, saddle points vastly outnumber local minima. A 2014 paper by Dauphin and colleagues showed that for a typical neural network loss landscape, almost all points where the gradient is 0 are saddle points, not minima. Vanilla gradient descent, with its 0 gradient update, will slow to a crawl near any saddle point. We need something more. Imagine a ball rolling down a hill. Even if it reaches a flat spot, it doesn't stop immediately. Its momentum carries it forward right through the flat region. We can add the same idea to gradient descent. At each step, instead of just following the current gradient, we accumulate a velocity that remembers the direction we've been moving. Beta is the momentum coefficient, typically 0.9. It means 90% of our previous velocity carries forward. The gradient steers, but momentum smooths the path and carries us through flat regions. Watch. Vanilla gradient descent crawls to a halt at the saddle. But with momentum, the accumulated velocity from the previous descent carries the dot straight through the flat region and down the other side. Momentum also helps in another way. It dampens oscillations in narrow valleys, smoothing the path toward the minimum. Momentum solves the saddle point problem, but there's still an issue. Different parameters may need different step sizes. A parameter with a consistently large gradient might need a smaller learning rate to avoid overshooting, while a parameter with tiny gradients might need a larger rate to make progress. This is the insight behind ADAM, Adaptive Moment Estimation. Published in 2015 by Kingma and Ba, ADAM keeps track of two things for each parameter: a running average of the gradient, like momentum, and a running average of the squared gradient, measuring how variable the gradient has been. Before using these estimates, ADAM corrects for initialization bias, dividing by 1 minus beta to the power t. Then the update divides the corrected momentum by the square root of the corrected variance. The intuition: if a parameter's gradient is consistently pointing in the same direction, ADAM takes a confident step. If the gradient fluctuates wildly, ADAM takes a cautious, smaller step. Each parameter gets its own adaptive learning rate. The default settings, beta 1 at 0.9, beta 2 at 0.999, epsilon at 10 to the minus 8, work remarkably well across a wide range of problems. ADAM is the default optimizer for most deep learning today. Let's see all three optimizers side by side on the same challenging landscape. A surface with a narrow valley and a global minimum. Ready, go. Vanilla SGD, in blue, oscillates in the narrow valley and makes slow, zigzagging progress. Momentum, in gold, smooths out the oscillations and moves faster, but overshoots slightly before correcting. ADAM, in teal, adapts its step size per direction, slicing cleanly through the valley with minimal oscillation. All three reach the minimum, but the path and the speed are dramatically different. When you hear that GPT-4 was trained on tens of thousands of GPUs for months, what was actually happening on each of those GPUs was this: compute the loss, compute the gradient, update the parameters. One step of gradient descent, every parameter update, every training iteration. The same algorithm we just watched a single dot perform on a simple surface, scaled to trillions of operations. In episode 1, we learned how AI represents the world as vectors and matrices. Today, we learned how AI improves by descending through a vast mathematical landscape, guided by the gradient. In episode 3, we'll discover how AI handles uncertainty with probability and Bayes' theorem.